Let's start. So last time we talked about triangle counting, right? It's kind of the one of the primitives that we use for graph analytics. And so today we're going to talk a little bit more about triangle counting. And I mumbled some of the things at the end of the lecture last time. So I mumbled about loading balance and so on. So today we're going to go deeper into it. And then we also would talk about multi-GPU parallelization. You know, when you start, you want to use multiple GPUs to do this kind of computation. You know, what are the challenges? And then we'll talk about the use case, which is the trust decomposition. Most of these analytics use the primitives, right? So you will be using some of these primitives as a kernel. So we'll talk about how some of these primitives are actually used in a real application, or at least a higher level primitive for the analytics. So this is where we ended last time. Right? That was the last slide, where we say, okay, we're going to be partitioning all our edges. So we take all the edges, and every thread will take one of the edges. And out of each edge, we're going to have a source and destination node, right? So in this case, one of the edges is going from node 1 to node 2. So we have the source and destination. And we go through the pointer, the row pointer. So the first one comes here, the second one comes here. And this gives us the beginning location of all the neighbors in the destination list, right? In that code, the column index array, which we call the destination array here. So 2 says the section for the neighbors of node 1 start from this location, right? And then the next one says it ends at here, right? And then this guy happened to be the next one, right? It doesn't have to be, but this happened to be the next one. So you come here, it starts at 5. So the neighbors start in this location, and then the next guy says the next nodes, the neighbors start at 7, right? So these two are the neighbors. So we know these 3 are the neighbors for node 1, and these 2 are the neighbors for node 2. So now we're doing the intersection. Okay, so we are in the position where we can do the intersection algorithm. So here, I walked through this, but I didn't really talk about the code. This is a pseudo code, and what we do is we use the U and V, right? These are the U and V, the node IDs for the source and destination. So the U and V, we will go into the P array, to find the beginning location of the neighbor list. So these are the P array accesses, right? So the P, you go to the PU and PV, and that gives you the initial value for the U pointer and the UN and the V pointer and the VN, right? So then you go into this loop, okay? You go into the loop. In each iteration, you ask whether or not I'm going to access the element, the destination number pointed to by UPTR and VPTR. So I'm going to ask, which one's bigger? Okay, and then also I'm going to ask, am I at the end of the list? Because if I'm at the end of one of the lists, I'm done. If you exhausted one of the list, there's no way you're going to find more intersection points, right? So you want to exhaust at least one of the lists. So I'm going to test whether the UPTR is at the end of the list, or VPTR is at the end of the list. If neither is at the end of the list, I need to continue. And then I'm going to compare between the W1 and W2, meaning I'm going to compare what's in these destinations. if W1 is smaller, I increment the U pointer. So this is, if the U element is smaller, I increment the U pointer. If the V pointer is small, element is smaller, I increment the V pointer until I find a match. If I find a match, that means that I found an intersection. I found the same element in both lists. And after this, I increment both pointers. Okay, I need to increment both pointers to get me out of that element, so that I'm going to be ready for the next next round of increment. And so, and also I found one of the triangles because I found the intersection, right? So then I go back and iterate. So let's walk through this, and see how the behavior actually looks. So let's use some arbitrary example. So in both, so let's say if U looks like this and V looks like this, okay, and it's a little bit bigger example, so we can show a few more kind of nuances and intricacies. So we start by U pointing to the beginning and V pointing to the beginning of these two lists. These are just two sections, right? Essentially two sections of that destination array, right? So we're at the beginning of each of these sections. And remember, we ask which one's bigger, right? We ask which one's bigger. So in this case, this is bigger, it's smaller. So we're going to increment the smaller one. We're going to increment the pointer of the smaller one. So we increment by 1 here, and suddenly 3 is bigger than 1 now, right? So you're done with incrementing the U pointer. So now you need to increment the V pointer. So the V pointer gets moved, and as soon as it gets 9, it's like, oh, now U is smaller too, again, right? Now U is smaller. So you will go and increment the U pointer. So you increment the U pointer, and from here you increment the V pointer, and then here you increment the U pointer again to 10. 10 is now greater than 9, and now you need to increment the V pointer. So you're ping-ponging the increment between the U and the V as long as they're not equal to each other. As long as one is bigger than the other, you don't have the intersection yet. And you know that you need to bring the smaller one up, right? And as long as the list is sorted, right? As long as the list is sorted, you can do this alternative increment. You know at some point you either exhausted all the elements in one of the lists, or you hit a intersection point, right? So now. So this is where we ended last slide. And so I would, so 9 is less than 10, so I increment. When I increment here, I find the intersection 10, right? I find the intersection, great. And then we need to increment both to get me ready for the next round of increment, right? So here, this is bigger, so I'll be incrementing on this end, so you would go all the way to 22, so now it's bigger than 21, and then you do the next round. So from 21, I increment to 27, and now it's bigger than 22, so now I go back and increment. So this is why we call this ping pong, the ping pong sequence, right? And here you have 32. Once you increment, you get to 32, and then you need to increment the V pointer. The V pointer now goes to 35, and you go from 35 to and up. Here, U pointer needs to be incremented. So now you have 35. It's like, aha, I have another intersection. So I have the second intersection, and then you bump both into the next position, 42 and 38. You start the next round, but at this point, because when as you increment 38, you go all the way to 41, and you exhausted this list. even though there's still ones that you have not looked at, it doesn't make sense to look at anymore because the fact that you don't have any more elements in one of the lists means that you can no longer find any more intersection point. Intersection point has to exist in both lists, right? So if we think about this, this sequence, there are a few things that we should notice, right? One is each thread performs sequential intersection on the neighbor list of the two nodes of an edge. So that whole sequence, that ping pong sequence, is done by one of the nodes, right? One of the threads, right? One of the threads. And there are many, many threads. Each thread is working on a pair of these things, right? Each thread is working on a pair of these things. And so there are, but within the thread, this ping pong increment is actually done sequentially. So that means that if the intersections for all the edges are done in parallel, right? So the threads, thread 1, thread 2, each one of them is doing this ping pong, but they may be doing very different ping pongs. So that also means that within the warp, they may have quite a bit of divergence.
Yes.
Okay. You may well have some pretty good amount of divergence. And that's one thing that you should kind of try to measure, okay, in your MP. Try to see how big a divergence these things are. Especially, and then there could be very significant load imbalance when the length of the neighbor list vary. Okay, and so let's say if one of the node has a lot more neighbors than all other nodes, then one of the poor thread is going to be doing a lot of that, right? And so you said, nah, maybe not. Maybe because the second list may be shorter, right? So you may exhaust the shorter list first, so it may be okay. But it's not exactly. So I'm going to show you that in the next example. Hey, Clint.
Were you in audio troubles with?
Yeah. So we're not able to get a microphone to work. So it seems to be transmitting to here. Hello, hello, hello. But somehow it's not coming out of the speakers.
Okay. Let's see if I can figure this out.
Yeah. So maybe the real expert. So I'll let you work on it while we deal with the intersection algorithm. So some of the threads can take much longer time to complete. So this is actually one of the most fundamental problems with parallel computing. Any time when you have a large number of threads and only a small number of threads are doing a huge amount of work and the other threads are not doing much work, your total completion time is limited by those a few small threads that are doing the vast amount of work. So this is the nightmare. This is also what I call the grading nightmare whenever we teach these courses. Okay, so the nightmare is that we have, let's say, 5 exam questions, and we have 5 people grading, and one of the questions got messed up. So you have all kinds of possible answers to that question that you have to give people credit for. So you have a poor TA who's grading that question, okay, and then everyone else is done, and the TA is still grading that question. And everyone else went to bed, and then the TA is still grading that question. But we cannot enter the grades until that poor TA finishes. You say, why not just have other TAs to help? Then you start to compromise the fairness, because now you have 2 different people grading the same problem. So then it becomes a policy and high-level decision about whether you are willing to have 2 different TAs grading the same problem, and they may use different standard, right? So we have very, very similar situation like this. Whenever you have a thread that is working on, a very large amount of work, then you always should ask the question, can I begin to have other threads to help, right? To be able to finish this critical long path of work faster, so that everyone can go home earlier. Okay, so this is thread 1 and thread 2, And so, this is kind of the simplified view of it, and say, okay, thread 1 is comparing two very long lists, and thread 2 is comparing, two very short lists for intersection. Therefore, thread 1 needs to do a whole lot more work than thread 2. But even you have a situation where only one of the lists is very long, the other one is short. It doesn't mean that you can terminate early. Okay, so this is a simple example. Let's say U is very long and V is much shorter. However, as long as the V, one of the V element is much bigger than all the elements here, you will end up having to increment the U pointer all the way through until exhausted, right? Exhausted U before you could quit. Right? So even though you may have a very short list, it depends on the value distribution. And you could have a situation where even though you have a very short list that's one of the inputs, you still need to go through the entire long list so that so that whole work is still there. Right? This is actually one of the challenges of graph type of computation. The amount of work that each thread does not only depend on the size of these lists and so on, it also depends on the value distribution. Okay, how the values are distributed. So this is the reason why in some of the algorithms, it actually matters how you assign the no ID. Okay, how you assign the no ID can actually affect the amount of work you do and also the loading balance. So that's why, remember when we did the total ordering, we talked about three possibilities, right? One is, we use we only preserve the edges when the source is greater than the destination. The other one is when the source is less than the destination. And the third one was actually degree. So we want to assign we want to preserve the edge when it goes from, let's say, a bigger degree node to a smaller degree node, or vice versa. These policies actually affect those values that you're going to see, okay, in these lists. And sometimes they have consistent effects, and sometimes they have kind of random effects, right? So these are the things that people actually, in the past several decades, there are PhD who spend their time thinking through these things and trying to prove properties or the statistical properties with these kind of things. Question?
Yeah. Can we create like a duplicates of U and share half of the load?
Oh yeah.
Because we only care about the sum, right?
Exactly. Yeah. So one possibility is that so let's cut this in half, right? And then have one thread to do the intersection between this one and this half, and the other thread does the intersection of this one and this one, right?
Yeah.
So then
and we know how long the gap is,
yeah,
right?
yeah. So that would be one strategy. In fact, that's actually one of the strategies that people do use to control this. Yes.
When you're restricting edges,
Yeah.
how do you compare the degree of the node without knowing yet how many outgoing edges it will have?
Oh no. This is usually in the pre-processing state. So you're actually reading in the entire graph, right? So that's why if you go back to the slide, I said that you need to have the whole graph. So the number of edges is the same. Okay, the number of edges is the same. However, depending on the direction of the edge that you preserve in that total ordering, you will change the neighbor list, the number of neighbors in the neighbor list, and also the values in that neighbor list, right? Because if you reverse the direction of an edge in your total ordering, then you are decreasing. When you do this, you're decreasing the neighbor by 1 for the original source, and increasing the number of neighbors for the original destination.
So in this case, degree is the total number of edges connected to the node, not the number of outgoing.
Right. So it's in the unidirectional sense, right? And then when you create the directional graph. Yes.
So if you consider this like pre-processing and if we require further computations
Oh.
based on this output, can we do like some kind of speculation? And
Mm-hmm.
when this result becomes available, we can substitute the value somehow, write that.
Yes, yeah, that, in fact, I think some of the methods probably do that. And they will take a guess and then, they say, okay, but when I work into it, if my assumptions are wrong, then I change.
Yeah.
So, I'm sure there's a paper about it, but I have not read it yet. Yeah, so, these are the, this is the reason why there's so many PhDs coming out of these kind of things. Because some of these properties, what they call the graph theory property, is actually quite interesting, depending on what you're trying to do. Because each different use case actually would have a different reliance on the graph property, right? So, if you, even when you go to some of these communications people, they actually do this all day long. They will say, in a wireless network, they will build a graph of all the devices and all the base stations, and then they have all the all the interconnects, and also their kind of their sort of the movement of the device across these base stations. So they build these graphs, and then they use the graph to prove some property about how the beamforming should work, and how the power will change if one hands over to the next, and then they prove some optimality. Okay, guess what? One of ours, the professor Haitham Al Hassanian, he actually proves these properties, and he gets papers out of these things, right? So these things are actually fascinating, and you can spend as much time as you want in these kind of things. So let's go into how we can how this can be a problem, right? We say, okay, if I have a very long list and a short list, as long as the short list, one of the elements in the short list is much bigger than the other list, or any of the elements of the other list, you will end up traversing through the long list. So here, let's say we start with 0 and 22, and 22 requires the U pointer to be incremented all the way to here, and say, I have an intersection, great. But then after the intersection, okay, both got bumped into 50 and 32, but from here, you will need to increment all the way to the end of the U list before you can end. So it doesn't mean that you have a short list, that list will be exhausted first, right? So this still will give you very, very long processing time. So what are the strategies that people make? So this is actually a good picture to think about these things. One good strategy is, well, if I have this very long list, remember all I want to find is the intersection. So I can just say, I can chop up the long list into multiple sections. And then the key thing is I need to take each of these sections and find the intersection with this V, right? So as long as the one of the lists is short, you can chop up the longer list, and then you will be able to to have reasonable amount of work with a shorter list, right? So that's easy. So that's a kind of a easy phase. And the second one is, well, what if you have a very long list here, right? If you have both lists are long lists, you could chop twice, right? You can chop this one, and then you can chop the other one. However, the complexity gets a little bit higher, right? You need to have 2 levels of chopping, and then you need to make sure that you have the combinatorial combinations, right, of intersection, right? But they still can be done. The point is they require different kernels, okay? You cannot write a single kernel to be able to do all the work. Yes?
But I feel like this process can be in the pre-processing. Like you do some maximum bounding when you pre-process and assign, like do those like.
Exactly right. In fact, this is exactly why people do no duplication.
Yes, exactly.
Okay, so what happens is that when people see these extremely long, the neighbor lists in these nodes, oftentimes what they do is they actually replicate these nodes. Okay, so that so basically what happens is this: you have a node that's, let's say you have two arcs coming in, and then you have 1 million going out. Right, so this is A. So what you do is you do A prime. You replicate the node, and then you have half of the edges coming out from here, and then half of the edges coming out from A prime. So the question is, what do you do with the incoming?
It has to be duplicated.
Right? So let's say if C comes here and D comes here, right? So remember, these two are equivalent, right? However, you need to make sure that if C comes here, right? If C comes in, you cannot just go to one of them, right? C will need to also be able to go to this one. Otherwise, C will lose half of the indirect nodes that it can reach, and then D will need to also do this, right? And so when you do the search, let's say breadth first search, where you do the intersection, you will need to have this. But if you think about it, this thing is exactly this thing, right? Because this is just a pre-processing that implements that policy, right? You have you're taking, in one case we're taking two threads. The nodes didn't change, but the two threads we're taking, each one take half of the destinations. And here, because we pre-replicated node, so that essentially we're going to be processing more neighbors here, right? But each one has a smaller number of neighbors, right? So these two are actually equivalent. This is a dynamic scheme, and this is a static pre-processing scheme. Sometimes you may not be able to always pre-process, so it will be a little bit easier to just use a dynamic scheme. However, on the GPU, traditionally, because this requires different kind of code, we will need to terminate the kernel, launch a different kernel to process this. But starting next week, we're going to talk about dynamic refinement and dynamic parallelism. That's exactly designed to allow this kind of further refinement. This is what we call the refinement, because you work into it, you realize that there's a lot of work that you need to do. So you actually, say, I'm going to further divide the work. We're going to launch a different kernel to do the work separately. So that's the dynamic parallelism. Okay. So that's one possibility, and then these two are exactly equivalent. And another way to do this, to think about this, is to say, well, do I really need to process all the, when I have a very long list, I can also use a different algorithm to reduce the computational complexity. Let's say if I only have a small number of these elements, there are only a very small number of intersection points possible, right? If you think about it. When the other list is much smaller, this is the upper bound of the intersection I can find. So I'm going to only find a very small number of points in a very long list. So what happens when you need to search through a very long list, ordered list, but you only have only have one or two of the potential hit, you do
Binary.
inner research, binary, trinary, whatever, right? It depends on how complicated you're willing to to go in terms of algorithm the algorithm code complexity. So I can just say, well, let's have two threads, right? Let's have two threads here, and each thread will be doing a binary search. So I take this guy, and I go here, I do a binary search, I take the middle, and say, oh, 22, so it's bigger than the middle point, right? And then I go here, it's this side, and eventually I come here, that's the one, right? So it's log n now, right? You will take log n steps for this guy, and then same thing, another thread will do the same thing, the other thread will also do the binary search, and eventually say, oh, I exhausted this, right? So essentially you come here and then say, okay, it's on this side, come here, it's on this side, and here it's this side, oh, it's not there, so I'm done, right? So two binary searches give me, and I don't even need to do, go through the entire list. And be careful with this, because when the second list is small, you have a small number. So let's call this n, and let's call this m, right? M is very big, n is very small. So when you have, essentially you will do n times log n operations in this in the strategy. So when n is truly very small, that's a good deal, because log n, essentially the log n squashes down the number of operations you need to do on this long thing, but then it's multiplied by the number of elements in the small one. As long as the m is very small, the product gets you a good deal, right? But if this thing becomes big, at some point, m times log n could be bigger than n, right? So then you start to lose, right? So that's why when you have two very long lists, it's actually not the same as a single, as a kind of a single long list and a short list. Okay. The other, so in that situation, what you should do is you should at least partition one of them, right? So if you, let's say if you start with two very, very, very long lists, it may be worthwhile to partition one of them so that each section is a small one, right? And then you would say, okay, so this is a small one, and then I can say for each thread I'm going to give a small section and then a long section to a set of threads to do this, but you will not fundamentally reduce the number of operations, because you still have to go through each of these smaller sections. On the other hand, if you have enough resources, you may be able to just use the parallelism to swallow it. But if you don't have enough resources, then you have no choice but partitioning this one. Okay, so those are the kind of all these alternative algorithm strategies that people will need to say, okay, what are the big ones, what are the smaller ones, and then we do the partitioning, and we do the choice. And that's the reason why, if you look at a very, very high performance code, oftentimes you will see tens of thousands of lines of code. You say, what? Where did all this code come from? And if you work into it, you'll start to see all these kind of cases. They're not because it's intrinsically so hard to do the operation, it's because they want to account for all these different scenarios and optimize the scenarios according to the number. The number matters in these things. Okay, yes?
Yeah, one more thing is like a further implementation could be you do a few pivoting before you do the inner research. You shrink down the range. Because for example, you have two values, you may look at the very beginning, middle, and end to kind of shrink down to compensate for the number of the
Possibly.
n elements.
Yeah, possibly.
N elements, sorry.
Yeah, so for example, you said here,
Because both are sorted.
right? Yeah, so you may be able to say, well, you know what, I don't really need to look at some portion here, right? So there, I mean, the amount of optimization you can do is actually really big, okay? So any other questions? Okay, good. So this is the, so now if we are interested, we're willing to do the analysis.
I don't think.
Yeah. Okay, sorry. Thank you. Okay. So I think we're going to end a little early anyway. So so for for the binary search, at some point if the list gets really big, you probably want to do a n-ary search so that you can converge better, faster. Especially if you can find if you know that you can do some kind of reuse of value and so on when you do the binary search. So that will become a customized search that you search for two elements at the same time when they're close in value and so on. Yes.
There are a couple of comments that I want to give.
Yeah.
The first comment is...
By the way, you guys need to try some of that.
Yeah. On that thought process itself, I'm actually speaking of. So the one on the node duplication, the problem with the node duplication that I can actually think of is you'll be increasing the memory footprint.
Yes.
If your graph is large, the node duplication can actually cause you to run out of the GPU memory. That's one problem that usually we run out of. On the n-ary kind of a search mechanism, there is a catch. So if you can actually do the search with the dynamic value on a parsing, like one jump you're going to do 4 jumps, in the next jump I'm going to do 2, then I'm going to do 1. That might be a good one.
Yeah.
But if you're going to do it a constant threshold one, the problem is you can't make it generalized, because some graph can have a good performance, and some graph you might have to do a multiple iterations to reach this particular endpoint.
Right. Yeah.
And that might actually cause you performance degradation.
Yeah. Exactly. Or in some cases, it may even cause errors.
It might even cause errors.
Yeah. Good. Okay. So let's talk a little bit about the multi-GPU parallelization. So a lot of times, people go for multi-GPU computation for these things for 2 reasons. Okay. One is each GPU usually comes with about a certain amount of global memory. So these are the DRAMs that come with the GPUs. So in the Volta generation that we have now, each GPU comes with still 16 or
32.
32 now. 32 gigabytes of memory for the high-end Volta chips. And so if you have a graph that requires more than 32 gig of space to be able to hold the graph, then you probably need to have 2 GPUs or more to be able to to hold that data. So that's a memory problem. And the other one is if you really need to have higher throughput, you need to use the more GPUs you have, the more potential throughput you're going to have, so that you can have faster processing of these very large graphs. So space requirement and also just the sheer number of nodes require more throughput to be able to process. So people would naturally try to use multiple GPUs to process the graphs. So if you look at this problem here, okay, so we have a graph. So this is a reasonably simple graph, and we say, how are we going to partition the data so that part of the data will go to one GPU and part of the data will go to another GPU, and hopefully, there's not a whole lot of overhead. If we need to spend a lot of overhead when we try to partition, then the benefit may not be that great, right? So one of the immediate things that we can do is that, remember, we have this edge list, right? Now we have this edge list. So we say, okay, we can just take the edge list and give each section. Okay, let's say I have 2 GPUs. I cut the edge list in half, give each of the edge lists to the 2 GPUs, right? So each GPU will have half of the edge list. And for triangle counting, that's a good start, right? So one GPU will be counting half of the edges, the intersection for half of the edges, and then half of the GPU will cover the other half of the edges. Sounds great. So what's the problem?
Communication.
Why would I need to have communication? You know what? Half of them are
Duplicate the middle.
calculating, half of the edges, and then the other GPU will be processing the other half. Why would there be communication? It has to do with this, right? Because every edge that one of the GPUs process involves 2 nodes, right? The source and destination of that edge. Is there any guarantee where those nodes can be? For anything that you pick up as an edge, the source and destination can be anywhere, right, in the graph, right? So that brings us to the partition of this part of the data structure, right? Because once you have the node ID of the source and node ID of the destination, you need to go to this data structure, right? You need to go to this data structure and find the neighbor list for those nodes, and then do the intersection. So one very simple thing to do is, let's just replicate this part of the data structure in both GPUs, right? We just replicate the P array, the ZD array, right? P array and ZD array in both GPUs. So each one will take the node ID and then just do the access. That will work. That will actually work. But what's the problem with that?
Your assumption, the reason why you use 2 GPUs is because you don't have enough memory.
That's right. So we did not replicate part of the edge array, but then we replicate this part. So instead of using half of the storage, essentially instead of using half each GPU for half of the storage, we actually need to accommodate something like 3/4 of the original storage. So the efficiency of increased storage capacity may not be that great, right? So, but this will be probably the easiest way for us to do this. Okay, at least we got rid of a little bit of the replication, and then we use the same data structure on both GPUs. Another way to do this is to say, well, I'm going to take, this is a easy, kind of an easy point, right? So this is the node list. This is essentially the same number as the nodes in my graph, right? So I'm going to take half of this thing, put it on one GPU, and half of this thing on the other GPU, right? And roughly half of this thing, right? Because this portion is going to be responsible for the first part of that D array, right? And then we're going to put this part, this second part, and the second part on the other GPU. That's a reasonable partition, right? So what's the problem? The problem is if you have an edge, you may end up in a situation where the node that correspond to the 2 nodes of the edge can correspond to one here and one here, right? So you may end up with 4 situations. One is both of the nodes that you need are on your GPU. That's a good situation, right? You're done. But then you can have one node on your GPU, one node on another GPU. Or you can have both nodes on the other GPU. So this is where the multi-GPU is a little bit different than the MPI, okay, program. When you have an MPI program, and when you distribute these things, they actually have to have their own address space. So they essentially each one becomes a smaller array of its own, Okay, so if you cut this in half and distribute part of it into one MPI node and another one in another MPI node, these two each become a smaller half-size array in your MPI code. And then you need to figure out how to associate that with the original bigger array. And then, so if you need any value from another node, you need to do a message. You need to request a message passing to get the data to you, right? So this is the, this is kind of the challenge for the MPI code when you try to do this. In multi-GPU, there is a little bit of a support here. The multi-GPU has a what we call the zero copy access or unified memory access. These two are actually different. The zero copy access means that one GPU can directly do a load access to another GPU's memory, okay? And that data eventually will come back. There's hardware support for the GPU's memory access to go to the memory controller of the other GPU, get the data, and then return to the requesting GPU. Zero copy works both between GPUs and between a CPU and a GPU. Okay, it's always GPU-centric, by the way. Zero copy is always GPU-centric, meaning that the accessing device has to be a GPU. Okay, so if you have two GPUs, the zero copy access can be done by either of the GPUs, and then they can access each other's memory. Okay. If you have a CPU-GPU situation, the only direction that makes sense is when the GPU tries to access the host memory, not the other way around. The host memory cannot use zero copy to access the GPU memory because NVIDIA couldn't convince Intel to change their memory controller. Okay, that's the real reason. Okay, so if you do this on a host, you have to declare the host memory as pinned memory. We'll talk about pinned memory in 408. You have to declare that memory as pinned data structure, and then the GPU pass the pointer to the GPU, and the GPU can do zero copy access to the CPU data. Okay? So in this case, what you can do is you can declare each part of the data. You can declare each part of the data structure as a zero copy access data structure, and then each GPU can just say detect whether it's in me or the other. If it's on the other side, you will do a memory load to the other side. You still need to detect it because you need to declare them as separate data structures so that each one can be a zero copy and map to the right GPUs. Okay, you cannot, as far as I can tell, there's no easy way to declare the first half of the array to be a zero copy in one GPU and the second copy of the second half of the array as a zero copy of the other GPU. I have not seen that interface. Okay, so you still need to declare them into two smaller data structures and declare them into the zero copy area of each GPU. And then the GPU, each GPU has to check whether it's in the right range. That is, the node ID falls into the range of its portion or not in its portion. So this can be done by checking the range, right? So if the node belongs to the first half or the second half, and then you do either the local access or the memory the memory access, sort of the zero copy access. So that's one way you can do this. It's a little bit of nuance. It's you need to do the testing, and you need to do the access, and with NVLink kind of interconnect, the bandwidth is actually very reasonable. Okay, you can get pretty good bandwidth accessing, for the GPUs to access each other's memory. there's a little bit of a nuance that zero copy usually does not work in a NUMA architecture. So if you have, let's say, 4 GPUs in your system, and 2 of the GPUs are connected to a CPU core, CPU, and then 2 other GPUs are connected to the other CPU. So for example, the IBM P8 and P9 systems are organized like that. Each motherboard has 2 power CPUs, and each one has 2 NVIDIA GPUs connected to the socket. And if you try to access, one of the, from one of the GPUs on a socket to the memory of another another GPU in a different socket connection, this usually doesn't work. Okay, so that's that's some of the limitations that you need to be aware of. The other way of doing, getting this to work is the unified memory. It makes the programming a little bit easier. You can declare an entire array. You can declare this entire array as managed in CUDA, which means that it's in the unified memory space. Whenever you declare this thing in the CUDA, as a unified memory data structure, this can be moved around on a page-by-page basis. So the CUDA runtime is going to try to detect which GPU is accessing this data and move the entire page containing that data to the right GPU. So in this particular use case, it's actually quite reasonable to declare this part as part of your unified memory data structure, because the first half will always be accessed by one GPU, and then the other half will be always accessed by the other GPU. So that's, if that, you can make that work, then it's fine. However, if your access pattern become more random, that is, in both GPUs, it's very likely you're going to have one GPU to want to access this guy, and then a little bit later, another GPU wants to, the other GPU also want to access this guy. Then you start to run into trouble. You start to have the page ping pong between the two, okay? Because they don't have coherent access, they don't have the option to replicate this to both GPUs. Okay, so that you will end up having the page being moved back and forth between the two. So if you have a situation where each one's accessing half of the, let's say half of the edge list, and if you look at the node numbers in half of the edge list, all the node numbers are concentrated on one half, and if you look at the other edge list and all the node IDs are concentrated on the other half, then this unified memory can work very well. But if you truly have some random distribution, then this is a bad idea. And you're going to get really, really bad performance, because it's not only going to move the data to the GPU, it's also going to move the entire page containing that data into the GPU. So every time when you access a piece of data, all the cousins, nephews, grandchildren, whatsoever, all move with it. Okay, and then you start to have what we call the data movement magnification. So you actually end up accessing a whole page without even knowing you're accessing the whole page. So for most of the situation in this kind of access, the zero copy should give you better performance than the unified memory. However, there's a very important programming difference. The zero copy means that you need to declare them as two separate arrays. You need to mess with the indices and so on to get the access to those little arrays to work. But in unified memory, you can still declare that as a single array, so your code can essentially remain unchanged. Make sense? So this is the reason why we actually do a lot of benchmarking and so on for every generation of GPU to understand the performance difference between zero copy and the unified memory and so on, because they actually have very real implications when you choose one or the other in terms of your programming complexity. Okay. And so whenever we use zero copy, the programming complexity is almost the same as the MPI programming. Effectively, we're declaring different data structures now, and then the accesses are becoming very similar to the message passing in MPI. Here, if we decided to chop this into half and this into half, then the performance definitely can vary depending on which side of the the access you're going to which side of the data you're going to be accessing when you try to do the intersection. So that's why when we do the node ID, the best way to in this situation is to try to allocate the node numbers so that all the connected nodes have similar node numbers. Okay, the node number assignment should be done so that whenever there's an edge between two nodes, their node numbers should be close to each other, right? And that will increase the number of localized accesses. So whenever two nodes of the same two nodes of that edge is processed, because these two nodes are connected to each other, we allocated the node ID to be very close to each other, and therefore they're more likely to fall into one side or the same side of that partition, right? So this is actually another very interesting area. So how do you mess with the node numbers so that your analytics can be more localized? Unfortunately, this is equivalent to a graph partitioning problem. Okay, this is not an easy problem. And then there are tools like methods and so on. So basically, you're going to need to do the partitioning of your graph. Conceptually, what you're really doing is you're going to be partitioning your graph, and then all the graphs in the partition will have essentially this sort of the numbers assigned in that range, and then the next partition will be all assigned in the next range, and so on, so that you can minimize the cross GPU or cross node accesses. This is the same for MPI and multi-GPU programming. Okay, there's no fundamental difference between MPI and multi-GPU programming. If you're doing MPI programming and you want to have some locality in terms of your messages, you do the same thing. You need to have a good graph partitioning algorithm. You pre-partition your graph and assign the node IDs consecutively within each partition, and then you connect all the graphs back together. Okay, so this is actually one of the very hairy part. That's why NVIDIA, even though NVIDIA can produce these multi-GPUs, they produce all these multi-GPU systems, they're still trying to build bigger and bigger GPUs. Because a lot of the code becomes so complicated when you try to make them into two multi-GPU system code. People just essentially give up at some point. So let's just make a few comments about how people use these kind of things. So I'm going to talk about the trust decomposition, which uses the triangle counting. So we talk about community, right? So when we first talk about the triangle counting, we said that graphs fundamentally give you the edge, and which is the relation between nodes, right? Pairs of nodes. So triangles are the first step that take you beyond two nodes. If you have another node involved, when you have a triangle, that means that there is a strong relationship between 3 nodes now, right? So the question is, how are you going to generalize into 4 nodes, 5 nodes, and so on? There are actually multiple ways you can generalize it. So one very intuitive way to generalize to 4, 5, 6 nodes is truss. So basically, if you have a truss, conceptually you will have a very, very intensely connected component where you have a very large number of triangles in that substructure. Okay, so that's the intuition behind it. You want to define it in a way that you have many